All right, everybody, happy Monday. I hope everybody had a really good weekend and good Mother's Day. So let's get into what we are doing this week. This week, you will be assigned lessons 11 and 12 from the most recent assigned work file. So if I open that up, you'll find 11 and 12 here. So if we go into lesson 11, there's this. This is going to be the actual work you do. And if you open that up, you're going to have to practice balancing equations. So you're going to select 5 of these chemical equations to balance so they follow the law of conservation of matter. So select 5 of the 10 here, and that'll be the work for this week. Though, you don't really know how to do that. So, in this folder, you're also going to see a PowerPoint right here. I've opened that up, and I want to go through that PowerPoint with you so you can see how to actually balance these equations. So, chemical equations, again, we've used them before to write our particulate models, but here we're going to really go in depth about how to balance them, because before we weren't so worried about balancing, we were just worried about translating them from particulate to chemical equations and vice versa, but now we're going to make sure we write them correctly. So here's an example of a chemical equation. Zinc and iodine form zinc iodide. So you're going to see that there's 1 zinc on this side, 1 zinc on this side, 2 iodines on this side, and 2 iodines on this side. That means it's balanced. So let's get into it. So chemical equations, again, are a model, and they depict the kind of reactants and products and the relative amounts in a chemical reaction. So these numbers in the front, 4, 3, and 2, the numbers are in the front are called coefficients. That's coefficients, kind of like the math coefficients, like 5x you'll see in your math class. So this means that there's 4 aluminum atoms. There's 3 oxygen molecules, so 6 total, because there's 2 oxygen atoms for every oxygen molecule, and if there's 3 of these molecules total, 3 times 2, that's 6. And then over here, we're going to see that 4 aluminum, 2 times 2, that's good. And then 6 oxygen over here, 2 times 3, 2 times 3. So it's balanced. So these green numbers are coefficients. The letters S, G, and L, and AQ, those are the physical states of the compound. So S means that's a solid, G means it's a gas, L, if it's there, would mean it's a liquid, and then AQ, let's say you see sodium chloride, NaCl, AQ, that means it's dissolved into solution. So anything that dissolves into solution is going to be AQ. That stands for aqueous. So let's talk about subscripts versus coefficients. So subscripts are going to tell you how many atoms of a particular element are in a compound. So for example, this O2 means that 1 molecule of oxygen consists of 2 atoms of oxygen, versus this O means that there's just 1 atom of oxygen. Same for here, they're kind of describing CO means this is what it looks like, CO2, there's 2 oxygens, but the coefficient tells you about the number or quantity, the number of molecules of the compound. So 3CO2 means that, well, we have these CO2 molecules, but we have 3 of them. 1, 2, 3. So don't get those mixed up. Coefficients are describing how many of a particular molecule or compound or atom, and the subscript 2 is whatever it comes after. There's 2 of them inside of each molecule. See how there's 2 oxygen in every single one of these CO2 atoms? And then there's 3 of them. That's the coefficient. The 2 is the subscript. So there are these certain elements that form diatomic compounds, and they're never found alone. So when we're talking about hydrogen gas, it's never hydrogen, 1 hydrogen atom by itself floating around. It's always 2 hydrogens bonded to each other in a diatomic molecule. So, for example, these are the diatomic molecules. They're always going to form a gas with 2 atoms. So H2, N2, O2, F2, Cl2, Br2, and I2. So that's the names of these elements. You're going to find hydrogen on this side of the periodic table, but then an easy way to remember it, starting with nitrogen, you just go to the right to fluorine, and then down to I. Okay? Johnstone's triangle. This is basically saying that chemists have a way to show reactions on 3 levels. These are our 3 models. We have our macroscopic level, we can see it with our eyes. We have our particulate level, which we practice a lot in school, showing the actual atoms reacting with each other. And then we have our symbolic level, meaning that this is our chemical equation model. Our chemical equation is symbolic. 2 coppers plus 1 oxygen gas, see how it's O2, that diatomic molecule, forms copper oxide, and 2 of them. So here's the idea of the law of conservation of matter or mass. So this is a really, really important concept for you to understand. And it's saying that in a chemical reaction, matter is neither created nor destroyed. We don't get matter coming from somewhere random, and even if a reaction happens, the atoms we start with are the atoms we end with. They just might be rearranged. Molecules can be converted and decomposed by chemical processes, but atoms are forever. Isn't that a nice sentiment? Atoms are forever. In a chemical reaction, matter at the level of individual atoms is always accounted for, and that means, for our purposes, chemical equations have to be balanced. That means the atoms on the reactant side, so what you start with, must be the same atoms as on the product side, what you end with. So let's see how that works. So if we have this reaction here, it's showing that if it's balanced, we're going to have the same stuff on each side. I would recommend using this type of chart. Like, you don't have to write it out this clearly, but hey, on this side we start with 1 silver, Ag. We start with 1 N. We start with 3 atoms of oxygen. See that subscript 3, 3O. 1 sodium right here, and then 1 Cl. And then a reaction happens. Same amount of atoms. It's balanced. It doesn't need any coefficients. We'll talk about examples of that later. And we're going to see that in this reaction, the mass starts the same in the products, and then the mass remains the same in the reactants. That means that no new matter is made or destroyed. The mass is the same, and that's proof at the macroscopic level of why this is true. We have proof at the macroscopic level, the symbolic level, or chemical equation, and at the particulate level that mass is not created or destroyed. It's the same atoms on each side. And then here's another example of that, this time with subscripts, right? We have 2 oxygen molecules, see that 2O2, so that means we have 4 oxygens to start with, 4 hydrogens and 4 carbons. Now if we go over here, 1 carbon. We also have 1 carbon on this side, and then we need 4 oxygens, so we have 2 in the carbon dioxide, so 2 plus the 2 from this water, 2 and 2, and then we have 4 hydrogens, 2 times 2 equals 4 hydrogens. So balancing equations, there's a process to this. It's kind of like a little puzzle. So if you're into puzzles, this is going to be your jam. So you need to identify atoms and do an atom inventory. So we see that kind of like this. Hey, these are the atoms we have in our reactants. These are the ones we have in our products. If they're the same on both sides, you don't need to add any coefficients. Add the coefficients in front of the compounds to balance the reaction. If those atoms on the reactants and products are different, you need to do some coefficient work to balance the reactions. What you don't do is change the subscripts. If you change the subscripts, you're changing the entire compound. Let's say you have an oxygen molecule right here, O2, and you want to say, oh, it's balanced, I'll just like add a 3 here to have this make sense. You don't want to do that because then you're actually changing what we're starting with. If you turn this into a 3, you would get rid of one of these oxygens and make it a 3 oxygen compound, which is not the case. So don't change the subscripts. The only thing you change is the coefficients in front of the molecules. So let's practice. So we have here 2 hydrogens, okay? We have 2 oxygens, and then we end with water, H2O. So 2 hydrogens, that's good. We don't need to add any coefficients for hydrogens, but we have 1 oxygen on this side and then 2 oxygens on this side, which is odd. So how are we going to fix that? Well, if we need 1 more oxygen on this side, we're going to put a 2 in front of this H2O. So it'd be 2H2O, but that also leads to another problem because then we're adding two more hydrogens. So 2 times 2, that's going to be 4. Okay, so now we have 4 hydrogens on this side and 2 oxygens. We need 4 on this side, so we'd add another 2 here. So 2 times 2 equals 4, then it's balanced. So the coefficients would be 2. Sorry, I can't type this in. 2, no coefficients, and then 2. How about this one? And here we can see it visually too. We have 1 aluminum, 2 bromines, and then we end with 2 aluminums and 6 bromines. Okay, so how about we add a 2 coefficient here? That would give us the 2 aluminums, and we see that here, 2 aluminums. And then to get 6 bromines, we need to add 3. See how there are 3 bromine molecules right here? 3 times 2 equals 6, and over here we have 6 bromines. And now we have different types of reactions. So this is a really helpful kind of picture of the different types. We have synthesis, 2 things coming together and forming one. We have decombustion, 1 thing breaking apart and forming multiple things. Displacement, you have 2 things bonded together and something on its own, and then sort of a switch happening. You can think of it like a dance, like if somebody wants to, 2 people are dancing, somebody, hey, can I dance with this person? Yeah, sure. They switch out. And then double displacement reactions. This might be more of like a fun switchy dance. I don't know what that would be called, but you have 2 compounds by themselves, and then, hey, they decide to switch partners. So for combustion, a combustion reaction is when oxygen combines with another compound to form water and carbon dioxide. So an example of this would be the burning of mothballs. Honestly, don't know what that is. So here you have carbon and hydrogen. It always has to be a carbon and hydrogen based compound, and then you're adding oxygen to it. That's why you need oxygen to fuel a flame. If you smother a flame, that's why you have throw a blanket over it. You take away its oxygen and it can't combust. But here we do have oxygen, and it forms carbon dioxide and water. And see how these coefficients are balancing out the equations on each side. Here we have synthesis, a reaction when 2 or more compounds combine to form a complex compound. So here's our example. We have iron and sulfur forming iron-sulfur. And that would be what? Iron 2 sulfur, because sulfur has a -2. This iron has to have a +2 charge. Iron 2 sulfide. Decombustion is when something breaks down to form simpler ones. And then an example of this would be water forming hydrogen and oxygen gas. See how those coefficients from before remain the same even though the chemical equation is reversed. And then single displacement. This is when one element trades places with another element in a compound. These reactions come in these forms. So we have zinc and copper to copper 1 chloride. So that's going to mean that what we see, this block, it's an arrow actually, but we see the copper switching out, breaking its bond with the chlorine, and then zinc comes in and bonds with the chlorine, and then the copper is by itself. So see how one is switching out with the other? Boom. And then double displacement means that we are going to have 2 compounds, and then 1 compound from each will switch places. So we have lead, let's see, that would be lead 1 nitrate, I think. No, lead 2 nitrate. And then we have potassium iodide, and then we're seeing that the iodine is joining with lead right here, and then the potassium will join with the nitrate right here, and then we'd have the coefficients balancing out. That's about it. If we're going to do an example here, let's see if we can open this up with Drive. Let's see. Open with Google Docs. Oh, this is tiny. Let me get it larger. I don't know why it's over here. There we go. So let's see, what would be a good one to do? Let's just do number 1 together. And then because I'm doing number 1, you can't do it. So number 1. And then I'm going to insert a little chart to help me stay organized. Let's see, insert chart, and then, or no, I'm going to do a table. Now I'm going to have reactants, products, and atoms. So there we go. Reactants, products. Alrighty. So we have our iron, Fe, and that's going to have 1. We have our hydrogen. There's 2 on the side, so 1 iron, 2 hydrogen. See that 2? And then with polyatomic ions, so something like SO4, you can treat that as one single thing because the S and the O4 are staying together on both sides. So again, here you can treat it like an element. If the O bonded with iron for some reason, then the S stayed with the H, you would not do that, but here we can do that. So SO4 we can treat as one thing, SO4. We have one of those on this side. Then I'm going to copy and paste that and write them over here. How many are there on the product side? So here, the iron actually has 2. And then the iron has 2. The hydrogen, there's actually 2 of them over here. And then the SO4, see how there's the subscript 3 after this? We have 3 SO4s. So if I'm going to write out my equation, oh my goodness. Oh, I shouldn't be writing on this. That means you guys have the answers. I'm going to delete this afterwards. So now we need to write out our equation. So iron, let's see, Fe, plus H2SO4. Let me make this a little bit bigger. There we go. 18. There we go. H2SO4. And then to make the arrow, I do 2 dashes and then the right arrow. There we go. Yields FeSO4 plus H2. So this is not balanced, right? Because we have different numbers on both sides. So the first thing I see I can fix is by putting 2 irons right here. And if I put 2 Fe here, I have to change that. Boom. Now, still not the same because you have 2 and 2, so the H is good. But then the SO4 is 1 and 3. So we need 3 SO4s on this side. So I'm going to add a coefficient 3 right here. Boom. So that gives me 3 SO4s. So that would go here. And then what that also does is it actually changes the amount of hydrogens I have from 2 to 6. So 3 times 2, that means we have 6 now. So we're getting close, but we need to fix this over here. So instead of the 2 hydrogens, you actually need 6 now. So I'm going to add a 6 right here. That changes the amount of hydrogens we have. Oops, not a 6, a 3. Because 3 times 2 equals 6. That's going to be 6. So 2, 6, and 3 on this side. 2, 6, and 3 on this side. This equation is balanced. Hooray! So you can't do number 1. You have to choose 5 others to practice on. But that's the gist of how you get this done.